Good evening. We have got a great deal to get through this evening, and so we will be very strict about keeping control. I will be. Can I welcome you all to the new Cavendish Laboratory? This is one of the first major events like this for the public that we've had. And so thank you so much for coming this evening. I am Malcolm Longare. I was head of the Cavendish Laboratory in 2002 when I persuaded the university that we had to rebuild the Cavendish Laboratory because it was falling down. And they said to me, "What an excellent idea, Malcolm. Go ahead and raise the money." Well, 20 years later, we managed that thanks to the generosity of the Ray Dolby family, of the University of Cambridge, and the Treasury, and that gave us the backbone, which was unstoppable, and this is what we've got. Thank you so much for coming, and I hope you will enjoy this wonderful new building. My next task is very simple. I need to introduce George Eustathio, who will introduce the participants in the discussion.
Shall I take the mic? Hi there. So apologies from Martin Rees, because he's a very busy man. He was double booked. And so I'm taking his place. I'm a lot less distinguished than Martin and not so busy, so I volunteered to do this introduction. Fortunately, we have a little video that Martin has made that we'll show after I've given this introduction. Now, when Fred Hoyle gave the opening address for the Institute of Theoretical Astronomy back in 1967, he said that the aim of the Institute was to discover new phenomena in physics by investigating extreme events in the universe. Now, this ethos is actually central to the scientific mission of the Kavli Institute of Cosmology. And phenomena don't come more extreme than black holes. And to put it into perspective, you know, the most powerful bang that we can get on Earth, a hydrogen bomb, we convert 0.7% of the rest mass into energy in the fusion of hydrogen atoms to make helium. But if we can tap the rotational energy of a rotating black hole, we can convert rest mass into energy with an efficiency of 42%, up to 42%. So we can explain energetic events in the universe powered by black holes. Now, with the discovery of powerful radio sources back in the 1960s, people like Malcolm Longare and Martin Rees pioneered the new field of relativistic astrophysics, explaining these energetic events using black holes. At optical wavelengths back in the 1960s, astronomers discovered quasi-stellar objects. So these are powerful, very luminous objects that can outshine all of the stars in a galaxy. And my predecessor as professor of astrophysics here in Cambridge, Donald Lindenbell, presciently offered the explanation that the energy of quasars was powered by accretion onto supermassive black holes. So in addition to extreme events, we now know that supermassive black holes are prevalent in the universe. Masses up to a couple of billion solar masses can form at the centers of galaxies, and all galaxies have a supermassive black hole as far as we know. So nature can convert about 1% of the mass of a galaxy and compress it into the volume about the size of the solar system. Now, you know, in this day and age, there may be people who can say, we can explain this. I can explain this in a day. It turns out that the problem is much, much harder. So we have three distinguished people that will guide us through some of the physics of supermassive black holes. Priya Natarajan here is a professor at Yale and one of our former students and the winner of this year's Daniel Heinemann Prize of the American Astronomical Society will tell us about the formation paths of supermassive black holes. Deborah Sajaki, who's Deputy Director of the Kavli Institute, will tell us how black holes can release huge amounts of energy that can alter the history of galaxy formation. And Roberto Maialino, who's Royal Society Research Professor here in Cambridge and was my successor as Director of the Kavli Institute, will show us how you can observe the effects of these outflows and potential merger events and so on through observations with the James Webb Space Telescope. So let me just say finally that the strong gravitational field around black holes can be used to test our understanding of the theory of gravity through gravitational waves, but also theoretically. There are important problems that Stephen Hawking first discussed about what happens to the information of the material that falls into a black hole. Is that lost? Does it come back out again? That can tell us about the nature of gravity. So black holes provide important clues to physics beyond Einstein gravity. And now I will hand over to our distinguished set of speakers. Thank you.
Well, thank you so much, George, and thank you, Malcolm, for the lovely introductions. And before we start this talk, you might have noticed that the QR code has appeared on the screen. So throughout the talk, if some interesting questions pop in your mind, feel free to scan the QR code now, and then you can post your questions in our Google form, and we will be very happy at the end of the talk to select a few select questions and try to answer them the best that we can. And now we start with a special treat, and that is a short video from Lord Martin Rees. So unfortunately, Martin couldn't be here with us tonight, but we were very lucky to catch him last night in the Trinity College and to do a short interview with him, and he will tell us all about what he thinks is exciting about the black holes and where the future is going.
General relativity was, of course, invented by Albert Einstein in 1915, but for the first 50 years after that, it became regarded as a rather sterile subject, and that's because there were no ways of testing it. Newton's theory was good enough for most purposes. But in the 1960s, there was a lot of excitement because the theorists got engaged, and more importantly, observations were made which indicated that these objects actually existed, and we could learn something about it. On the theoretical side, there was a lot of activity in Cambridge, and the two best-known figures were Penrose and Hawking, and there were others in a group together at that time, and I was on the fringe of this because although I was interested in their work, I was more involved in actually doing the phenomena of what happens around black holes than the actual geometry of the black holes itself. But in the 1960s, objects called quasars were discovered, where it was clear there was some source of energy in the center of galaxies, which outshone all the 100 billion stars in the entire galaxy. And these quasars, so-called, were discovered in 1963, and many, many after that, of course. And so they were interpreted by some of us in the 1960s as being caused by gas swirling down into a black hole, getting very hot indeed as it falls in and releasing lots of energy. By the end of the 1970s, that idea, which originated with two Russians and with Don Lyndon Bell, was now being taken very seriously, and people wanted to work out more details. And I did some of this, working out what it would do to produce jets and what sort of X-rays you would get, etc. So that became a subject which was being studied, the phenomena that happen in galactic nuclei. But then, of course, the other question is, how do they form? And here again, there are lots of different ideas, in fact, in a lecture I gave in Oxford in 1977, I plotted out a diagram of all the ways that could form a massive black hole. So it's a sort of flow diagram, and the bottom line in big type was massive black hole, but there were lots of routes which were possible ways in which matter could agglomerate, ending up in a massive black hole. And this was something which has been developed, and most of those routes are thought to occur somewhere or other. And of course, we have many new phenomena like gravitational radiation, which are associated with some of these objects. So this is a way in which we came to understand how black holes were crucial in determining the structure of galaxies and providing the most luminous objects in the universe. But one general consequence is that black holes can't be bright for their whole lifetime. There's lots of reasons why a black hole may be bright for maybe 100 million years, but that's only 1% of its likely lifetime. And so what one wanted also was some way in which you could detect the presence of a black hole when it was in its quiescent phase, because most such black holes are in that stage. And I suggested, again, around 1980, the idea that occasionally a star might wander too close to a black hole and be torn apart by tidal forces of the black hole, and the debris of this star, which wouldn't have been bright enough to see normally, would be spread around and would radiate very much, and you get a flare. And indeed, X-ray astronomers in particular have found lots of flares.
And are you excited about the developments that you're seeing now? Could you have anticipated them?
Yes. I talked about the things that excited us in the 60s and 70s and 80s, but of course what's happened since then is two things. First, the development of powerful computers, so we can now do experiments in the virtual world on black holes, colliding them, crashing galaxies together, etc. And of course, in a science where you can't actually experiment directly, it's been hugely advantageous to be able to do these experiments in the virtual world of our computer. And that's hugely advanced our subject. We can now study in much more detail how gas flows into black holes, and also another exciting new subject, what happens when two black holes get too close to each other and merge. Because that's led to another completely new channel to observe the universe, namely what's called gravitational radiation. If two massive objects, best of all two black holes, are orbiting around each other, then they radiate gravitational waves, literally ripples in space and time, which move outwards and take energy away. And so the binary black hole will eventually merge into a single big black hole and will produce the gravitational radiation which carries away the energy. And of course, this is very, very hard to detect because the amplitude of the ripples is incredibly small. But within the last 5 years, an experiment called LIGO in particular has been able to detect literally hundreds of events where you see a burst where there's a sort of ripple in space-time of a predictable character which can be detected by this very sensitive equipment. And the equipment, incidentally, consists of two sets of mirrors separated by 4 kilometers, and light from lasers goes backwards and forwards, and one can measure a tiny displacement of the mirrors as they oscillate. And to see how incredible this is, it's like measuring something the thickness of a hair at the distance of Alpha Centauri, 1 part in 10 to the power 21. And this exemplifies another point which I think all theorists like me ought to emphasize, which is that what has advanced our subject is technology and instrumentation. Armchair theory helps a bit, but it's the instrumentation which has advanced the subject and led to these wonderful discoveries.
Okay, excellent. So we want to start with this talk telling you about something very special. So there is a wondrous thread that connects different centuries, and it also weaves through different disciplines. And due to this wondrous thread, we actually sometimes made unexpected discoveries, and this is really what excites us as scientists. An example of such a wondrous thread is this visual here, which is a visual of something which is called the Penrose tiling. And the Penrose tiling is a special way of tiling which doesn't have repetitions in itself. So famously and really excitedly, Johannes Kepler, famous mathematician and astronomer, has studied this Penrose tiling. But later on, very unexpectedly, this tiling has been inspirational to understand structures which are called quasi-crystals, and that led to the Nobel Prize in chemistry, actually. So now, coming to the black holes, so the black holes are exactly this type of phenomena that lie at the intersection of disciplines. So they need extremely complex mathematics so that we are able to explain them. They lead to a variety of high energy physics phenomena, and also in terms of astronomy, they lead to many different objects. They lead to some these lurking dormant black holes that Martin Rees mentioned in his talk. But at the same time, they lead to the most energetic objects that we know in the universe, which are called quasars. And in this little visual here, you can see what an observer, if we were so lucky to see the light that is orbiting around the black hole coming back at us. And you can see these last bits of orbits of a couple of photons. They can orbit around black hole and escape just before the event horizon and still reach us. Now. So now a little bit about the history around black holes. So I think the only right way how to start with this is mentioning Albert Einstein. Famously, in 1915, Albert Einstein proposed his fundamental theory of general relativity to the Prussian Academy of Sciences. And very remarkably, just like a month after, Karl Schwarzschild wrote him a letter where he provided the first exact solution to the Einstein field equations that corresponded to a spherical, non-rotating object, which caused a huge deformation in space-time. And this object is what we call nowadays a black hole. Another miraculous year for mathematical understanding of black holes was done in 1963 by Roy Kerr, who developed another exact solution, this time for an object that can rotate around its own axis. And these exciting mathematical discoveries has then led to a huge impetus, both in theory and observations in 60s and 70s, where this whole field started to flourish. So now we are extremely proud and have amazing heritage to have a number of Cambridge pioneers, scientists, that have provided fundamental insight into the black holes. These insights come both from the mathematical side, understanding how space-time bends all the way within event horizons in the black holes, but also providing huge astrophysical understanding of these black holes. And as Martin again mentioned, for the first time here in Cambridge, we have led to the ideas that actually the matter and the radiation swirling around the black holes can lead to some of the most energetic phenomena in the universe that we call quasars.
And as you all know, black holes have a real hold on our imaginations. And we imagine them as cosmic vacuum cleaners, swirling and gobbling everything that we can see. And black holes have, of course, inspired art. They have inspired fiction, anime, what have you. So let's start to try and understand what these objects are. What are they? And there are multiple ways to think about black holes. And so I'll just take you through 3 different ways to think about them. One of them, as Deborah mentioned, these are actually extremely compact objects where mass is concentrated, and they are so compact that they actually bend space and time. And that's one of Einstein's theory of general relativity's posits, that gravity is actually an interplay between matter and the shape of space. And the deformation Every object that has matter creates deformations in space-time, and the deformation that a black hole creates actually encases a singularity, a place where all known physics actually breaks down. Another way to think about black holes is the intensity of their gravitational pull. As you all know, launching a satellite, a rocket from the surface of the Earth takes the velocity with which you boost them has to be about 11.2 kilometers per second. It turns out the intensity of gravity around a black hole is so strong that you need to launch something with the speed of light. And that is the cosmic speed limit, right? So that's why they're so enigmatic. And of course, the astrophysical way, how black holes really became objects of study in astronomy and astrophysics, with the wide amount of phenomenology across wavelengths that we now use to study them, they're actually the end states of stars. Stars whose birth masses exceed 25 times the mass of our sun or so will end up after a nice, colorful life, giving you these very compact objects, these stellar corpses. So now you have three different ways, and we as scientists actually move between these three kinds of definitions as it suits us, depending on the phenomenology that we are trying to understand around black holes. And another way to really visualize, so this is a beautiful visual that gives you the sense of the compactness. And so what you see here is the relative size of this region, this event horizon from which not even light can escape. That's the sacred boundary of the black hole. You can see that for nearby black holes that are harbored, as Deborah mentioned and Martin mentioned, they appear to be harbored in the center of almost every galaxy in the nearby universe, at least, if not every galaxy in the entire universe. So now you see the depiction in this beautiful visual of the sizes, the sort of event horizons, and the regions from which radiation can be received from these black holes. Remember, light that you see, and Deborah showed in the first movie, that's light that is coming from well outside the event horizon. Obviously, light, if it were crossing the event horizon, would never be seen again. So here you get a very nice visual in terms of the scales that we're familiar with our own solar system. And then black holes also come in many kinds, and the key properties for a black hole really are the mass, its spin, and its charge. And the charge is not astrophysically interesting for us quite yet, but the masses with which black holes are born, we find that there are categories of black holes. There are stellar mass black holes that are most likely those corpses that I discussed earlier. Then you have these intermediate mass black holes whose mass range is between 1,000, few hundred to 1,000 to 10 to 100,000 times the mass of the sun. That's a very elusive population. And what we know are ubiquitous are the supermassive black holes, whose masses are 1,000,000 times the mass of the sun or above. And it turns out the universe is littered with black holes of all these kinds.
So now to continue our tale about the black holes, I want to convince you that we are now experiencing a golden age of black hole science and black hole discovery. And I want to start this illustration by telling you a tale of two Nobel Prizes. So one regards a painstaking and many decades of a study about the supermassive black hole in the center of our own galaxy, the Milky Way. So in this background image, you can see a beautiful image of our Milky Way galaxy. And then if you imagine zooming into center of the galaxy, there is extremely dense region filled of stars in there, but at the very, very center lurks our own supermassive black hole. So how did the scientists measure to determine the mass of that black hole and to convince us all that this is really a black hole and not some other phenomena? So they took many years of resolving and following orbits of stars around the black hole in the center of our own very galaxy. So from the orbits of these stars and how fast they move, we can deduce the mass of the central object that makes them orbit around. But what is really remarkable here is the vicinity of these stars to the central black hole. And that tells you that this has to be so compact that we know only of one physical object that can be so compact and having that mass, and that is a black hole. Another remarkable Nobel Prize came from this amazing discovery of gravitational waves. This, again, took 3 to 4 decades to be able to measure this. So it's really amazing that we can actually do this. So what we are talking about here we have actually 2 stellar mass black holes that are orbiting each other. And as they come closer and closer, what we call an in-spiral, there are these ripples in space-time that Martin Rees mentioned that are generated because there is a huge deformation in space-time. So as they come closer and closer, these ripples become stronger and stronger. And finally, in 2015, for the very first time in humanity, we have managed to detect this very difficult signal. And that is a telltale sign of general relativity. So this is an amazing discovery. But not only that this team of scientists managed to discover that, they have discovered a huge set of objects, stellar mass black hole mergers. So we have now a statistics on them. We know this is not a rare phenomena. And also, as Priya has mentioned, we have now excitedly entered this realm of intermediate mass black holes, which we were not sure they exist at all in the universe, because through gravitational waves, we can for the very first time detect them.
So the obvious fundamental question is, how do black holes form in the first place? And how do they actually grow? And you may remember the clip where Martin was talking about this diagram, which has massive black hole written in the bottom. So I think what is remarkable about this diagram is that he and others were thinking about how to make supermassive black holes well before there was evidence accumulating for them. So here you see a sort of range of physical processes, many of them revolving around stellar corpses and the pathways as a pathway to form the first black holes, and then eventually grow them to be more massive over time. And what we now know from understanding these many black holes, populations, not just individual sources, but populations of black holes that have been detected as quasars, we know that they grow by accreting matter. And we have seen, for example, up close, a couple of black holes that the Event Horizon Telescope collaboration was unearthed. It was that donut image that you have probably all seen. And that is as close as we have ever, as humans, gotten to glimpse the radiation coming from a black hole. And what we know from this image is that our idea, and what you just saw in a simulation, our idea of the gas, the accretion disk that powers the black hole and powers these jets that we also see, is really coming from right around the black hole, outside the event horizon, a few times outside the event horizon. And coming back to Cambridge, so it turns out Cambridge makes an appearance multiple times in the story of our understanding of black holes. This is a photograph of Einstein and Sir Arthur Eddington sitting outside Cambridge Observatory. And Arthur Eddington made some real seminal discoveries of his own and contributions to theoretical astrophysics. But he's probably most famously known to all of you as the person who bought Einstein's very radical idea of general relativity and was instrumental in finding observational evidence. He found the first compelling evidence that GR was correct. Aside from that, he did something much more fundamental, which is really shaping our understanding of how black holes grow, which is he realized that a compact object like a black hole, if you imagine a cloud of gas, electrons, and protons around it, that there is a delicate balance between the gravitational pull of the black hole and the pressure that this radiation that comes from this black hole, rather efficiently converting matter into energy that George mentioned. That delicate balance is called the Eddington limit. If you will, it's an optimal feeding limit for black holes. And that we credit to Eddington. And many of the black holes that we see in the universe appear to respect and honor the Eddington limit, but not quite. You'll hear about that a little bit later.
So even that it appears, as Priya has just mentioned, that the Eddington limit seems to be fundamental and telling us something about the growth and luminosity emanating from black holes. Actually, the lives of black holes and how they grow is a function of cosmic time is much more complex. Notwithstanding that, there is this amazing relationship between black holes and their host galaxies, which is extremely simple, but at the same time very puzzling. So what we are showing you here on this plot, it's on the x-axis, you have the mass of the galaxy, which in its center hosts a black hole, and on the y-axis, you have the mass of that black hole. And there seems to be a very tight correlation between these two quantities. So this is really puzzling us. Why is that the case? Because we have just told you black holes are so compact objects. So why a compact object as a black hole should care about the properties of entire galaxy and how entire galaxies could be possibly shaped by such a tiny compact object as a black hole? So we have an answer to this, or our best bet, what it is, and that comes through cosmological simulations. So these are the simulations where you discretize in a code many thousands of lines, and you try to run the simulation on high-performance computing facilities, and what you get is a virtual universe. And in this virtual universe, we can see how galaxies form as a function of time, how they grow in mass. But these galaxies that in this particular simulation also host black holes in their center are completely transformed by the presence of these black holes. So what is going on here? As the galaxies grow, the matter manages to swirl around the black holes, and that releases a huge amount of energy and radiation. It heats the gas, it pushes the gas out, and you see these powerful kind of explosions coming out, and this transforms the galaxies and leads to this relation between the black holes and galaxies.
So what has really exploded in the last decade or so, along with the wonderful deluge of data that we've had, is the sort of understanding, theoretical and computational understanding, as Deborah just showed, with sort of state-of-the-art computers, but also conceptual models and new conceptual models for how the first black holes could have formed. And so you may remember Martin Rees's diagram. So it turns out that in addition to the sort of pathways that he discussed, many of which involved the formation of a supermassive star and then that leaving behind a corpse, we now believe that there are many cosmic environments in which black hole formation can occur with some degree of efficiency. So these sites can be star clusters. So for example, you could have stars, the first stars that form in the universe, they are more massive than the stars that are forming today. They leave behind a little stellar corpse. And those stellar corpses could grow even at the Eddington limit and give us the supermassive black holes that we see ubiquitously around every galaxy in the universe. So the challenge is, where do you start? How big a black hole do you have to start with to explain the million, billion solar mass behemoths that we are seeing in the centers of galaxies? So you can see here sort of a sequence, a vignette that shows you the kinds of numerical computations. These are very, very difficult calculations to see how you could make the first black holes. And so one particular scenario that has been very intriguing is a process called the direct collapse of gas, which actually circumvents the formation of a supermassive star. And this scenario is testable. And I think this is one of the projects for many computational groups around the world to try to see, even if we can't make a black hole ab initio in one of these simulations, how close we can get to simulating the various pathways for black holes. And not the least, as was mentioned earlier, Stephen Hawking had something very interesting up his sleeve in the 1970s. Stephen Hawking and Bernard Carr proposed that we actually don't have to wait so long in the universe to make the first black holes. We could form a class of primordial black holes that likely formed right after the Big Bang, right at the get-go of our universe, and that they kind of coasted along and eventually started growing when the universe started being dominated by matter. And we believe now that this idea has had a huge resurgence because we believe now that this is another plausible pathway that we should consider.
So to tell you a little bit more about these new pathways, we are now understanding that we have to understand the physical processes that lead to black hole formation and the growth much more accurately. And here in Cambridge, we have spent last 10 years developing latest numerical algorithms and models that allows us to simulate not just entire galaxies, but to zoom in further and further, to zoom in exactly in these dense centers, one star at a time, follow the evolution of every single star, understand what these stars are doing, understand what the gas is doing around the stars, how the gas ultimately is swirling around these black holes, and how it leads to this black hole growth. And this is a really tough numerical challenge, but we are making amazing progress. And also, this progress is much needed because of something that Roberto will tell you right now.
So if you want to test these theories, these models, you need data. You need astronomical observations. And specifically, if you want to test these scenarios about the formation of the first black holes, you want to look into the past, into the remote past, when at the epoch when the first black holes formed and started their growth. And we have the perfect time machine for this, the James Webb Space Telescope, or JWST in short. This is the largest telescope in space, and it is so powerful that it can see faint, very distant galaxies in the early universe. But we are not seeing these galaxies how they are now because of the finite speed of light. We are seeing these galaxies how they were when at the epoch when the light was emitted by them and started their journey towards us. So, and in the case of JWST, we can see galaxies how they were billions and billions of years ago. And it's not really a metaphor. With JWST, we can really see into the remote past, and therefore we can look at the epoch of the formation of the first black holes and how they grew across the cosmic epochs. And to give you an idea about the fantastic leap forward enabled by JWST, this is a group of distant galaxies observed with a large ground-based telescope. And this is the same patch of the sky observed with the JWST. And you see that those blobs are now actually turned out to be fantastic, beautiful spiral galaxies. And this is thanks to the sharpness of the JWST images. But not only, the sensitivity of JWST allows us to see many more distant galaxies than what was possible with the ground-based telescope. And JWST is actually far superior also with respect to its predecessor, the Hubble Space Telescope that you may have heard about. And this is, again, a distant galaxy observed with the Hubble Space Telescope. And this is the same galaxy observed with the James Webb. And you see that that blob has now showed these fantastic spiral arms. And again, we see many more faint, distant galaxies than what was possible with Hubble. Of course, with Webb, we are not only seeing very distant galaxies, we are also finding a plethora of distant black holes. These are two of among the most distant, which are observed at an epoch when the age of the universe was only a few percent of the current age. And it's not that we are looking for these distant black holes just for the sake of it, just to break a record. These distant black holes are highly informative about the early seeding, early formation of these black holes. And indeed, their properties are quite intriguing. To begin with, they're already very massive, very early in the universe. And this is shown in this diagram, which shows the mass of these black holes as a function of the cosmic epochs at which they are seen. And so you see that some of these black holes have already masses of several million times the mass of the sun, already within the first few million years after the Big Bang. It may sound a lot, but actually is just a very short time compared to the current age of the universe, which is nearly 14 billion years. Okay, and those blue lines essentially show an attempt to reconstruct their growth back in time, assuming the stream hypothesis that they have always been accreting at the maximum limit allowed by this theory that Priya mentioned, that is the Eddington limit. And you see that it is essentially impossible to reconcile the formation of this black hole with the standard paradigm whereby these black holes originated from stellar remnants and accreted at the editor limit. You have to invoke, therefore, the only possibility is that these black holes were born big, and there are theories that predict that, as Priya mentioned, or that there were reckless black holes that somehow they managed to circumvent the legal limit given by Eddington, and so they managed to grow much faster. The other very puzzling finding about these black holes is the environment in which they live. As Deborah mentioned, in the local universe, we find that these black holes live in very large galaxies. And despite being supermassive, actually, they make a very little contribution to the overall mass of these galaxies. They are typically about 1,000 times less massive than the host galaxy. On the contrary, with Webb, we are finding in the early universe black holes which are much more massive than these relations. Some of these black holes are nearly as massive as their host galaxy. And for us astronomers, this is really mind-blowing because it tells us that somehow the universe manages to create these monsters in these tiny galaxies. And amongst these, this is probably the most extreme and the most puzzling, which we have been studying recently in Cambridge, and is a black hole, a very distant black hole, for which we actually cannot see much of a galaxy around it, just a little bit of gas. And as far as we can say, this is a nearly naked black hole. And for certain, we can say that this black hole is more massive than its putative galaxy, if there is any galaxy around it. And so this is really a paradigm shift, because the standard paradigm until recently was that you form galaxies and then black holes form and grow inside them. But this black hole actually seems to have formed first, and then probably the galaxy will form around it. So it's really a phenomenal discovery.
So talking about paradigm shifts, there is another very interesting aspect around black holes. So we know within our cosmological structure formation paradigm how our universe has formed, that small mass galaxies form and then they merge together to form larger objects. And we have some spectacular examples of mergers of galaxies in the local universe. But we know in the local universe, this process is not very common. However, when we switch to the high redshift universe, at the early cosmic times, the infant universe, galaxies are merging all over the place. It's really amazing. So this is a picture from JWST again, and you can see these different groups of galaxies orbiting each other, swirling around, destroying each other in the process of merging. And we think this process is really, really common. So we now, as theorists, we want to understand this, we want to understand what's going on. And here I'm showing you a nice visualization done here in Cambridge, where we can actually study these JWST-like galaxies in our supercomputer, and we can understand how these galaxies orbit each other, on which timescales do they merge. But not only that, we now expect that each one of these galaxies, these bright spots surrounded by this diffuse blue gas, is hosting actually a black hole in its center. So as the galaxies merge, the black holes should merge too.
And we are finding these galaxies, merging galaxies with their black holes with JWST. This is a spectacular case that we found last year with the James Webb, where it's a very distant galaxy, essentially recently merged, and we see two black holes inside it, which will merge very soon. And we actually are recently finding many more of these, and so these can actually, the merging of the black holes in the early universe can be an additional channel through which black hole can grow very fast.
So coming again to the mergers of these black holes, there is a whole new field that is opening ahead of us. So as you can imagine, these black holes, similar to the stellar mass black holes that we showed you before, are orbiting now each other. But as they are orbiting each other, the gas is swirling around them and around them. So we expect a lot of electromagnetic radiation waves coming to us, to our telescopes, so we can observe that. But very excitingly, when these black holes start coming closer and closer together, eventually we will enter into the regime that they will also produce these ripples in space-time. So we will detect gravitational waves in the future from these black holes. And this leads us to our final finale of the talk.
So all of this is very exciting, but the future maybe is even more exciting. Indeed, there will be new facilities in the future which actually will open new discovery spaces. One of these is LISA, a new space mission recently approved by the European Space Agency. And this fantastic space mission, in about 10 years from now, will be able to detect the gravitational waves produced by these supermassive merging black holes in the first few 100 million years after the Big Bang. On ground, the next big leap forward will certainly be the Extremely Large Telescope. As the name says, is a gigantic telescope with a mirror of nearly 40 meters in diameter, and in some bands will be even more sensitive than James Webb, and certainly will produce images much sharper than James Webb. And so we are not building this next to the Colosseum. This just to give you a scale of the size. It's been actually in advanced stage of construction in Chile, and will start operation in a few years from now. And just to give you an idea of the leap forward enabled by the Extremely Large Telescope, this is an image of a distant galaxy with James Webb, which we have been praising so much, and so on. But this is the same galaxy seen with the Extremely Large Telescope, and you see that you now can resolve with extreme details all of its features, and we will also be able to understand and trace the physics of the black holes in their cores.
So there you go. You've heard the sort of story of black holes, where we started with very simple ideas, and more data led us to have to think about them in much more complex ways. And we were able to answer many fundamental questions about how black holes are born, how they form in the first place, what is the origin of supermassive black holes. And as Deborah and Roberto have shown you, that they grow through accretion of gas and merging and crashing into other galaxies. So some fundamental questions are answered, but you know how science is. You answer some questions, and that opens up many more questions. So here we are at the precipice of a very, very exciting time with all these new facilities that Roberto just showed you a glimpse of, and how we can peer deeper and deeper into the universe. As you know, data is the ultimate arbiter of our ideas. And of course, in cosmology and astrophysics, since we can't perform controlled experiments, the kind of work that Deborah does is foundational. You can simulate the universe on your screen, on your computer screen, on your laptop. So we await with bated breath, right, guys, with what is coming down the pike in the next 5 to 10 years. Thank you so much for your attention.
Thank you.
It was a pleasure to have you.